Hello everyone. In the architectural history of Chinese civilization, the Great Wall and the Fujian Tulo stand as two monumental achievements that have endured for centuries. As you can see in these two images, despite hundreds of years of weathering and erosion, they remain as solid as ever. Archaeologists have found that the reason these ancient structures have resisted the erosion of time lies not entirely in hard stones, but in a magical white, cementitious material filling the gaps between the stones. This material is one of the earliest cementitious substances used by humans, lime. Today, we will travel back to ancient construction practices and, from the perspective of modern science, re-examine three non-hydraulic cementitious materials: lime, gypsum, and water glass. The key topics of this chapter include the technical requirements, properties, and applications of lime, the technical requirements, properties, and applications of gypsum, and the properties of water glass. One of the main challenges lies in how to distinguish the similarities and differences in properties between lime and gypsum. With the following two questions in mind, let's explore this lesson. First, we need to clarify what cementitious materials are. Simply put, cementitious materials are substances that can bind granular materials, such as aggregates, into a solid mass. They can be classified into two types: inorganic and organic. According to their hardening conditions, inorganic cementitious materials are divided into two categories. One, non-hydraulic cementitious materials. These materials can harden only when exposed to air and maintain their strength only in air. Examples include lime, gypsum, and water glass. They are generally not water resistant and are suitable only for dry environments. Two, hydraulic cementitious materials. These materials can not only harden in air, but also harden and maintain their strength in water. The most typical example is cement. Next, let's focus on distinguishing two core concepts: non-hydraulic and hydraulic behavior. How do we tell them apart? A simple way is to look at their survival environment. The first category is non-hydraulic cementitious materials. Typical examples include lime, gypsum, and water glass, as mentioned earlier. Their defining feature is that they depend on air and cannot tolerate water. They can only harden and maintain their strength in air. Once immersed in water, they lose their strength. Therefore, they are only suitable for dry environments above ground. The second category is hydraulic cementitious materials. The most typical example is cement. It is characterized by being amphibious. It can not only harden in air, but can also harden and even perform better in water. As a result, its applications are extremely broad. Whether in above ground, underground, or underwater engineering, it performs reliably. So, how is lime produced? As shown in the figure, its raw material is limestone, whose main component is calcium carbonate. The production process is straightforward: high-temperature calcination. When the temperature reaches about 900 degrees Celsius, calcium carbonate decomposes, producing carbon dioxide and calcium oxide, which is commonly known as quicklime. In addition, the raw material often contains a small amount of magnesium carbonate. This compound decomposes earlier at around 700 degrees Celsius, forming magnesium oxide. Therefore, the production of lime is essentially the thermal decomposition of limestone at high temperatures. However, in actual production, due to uneven temperature control, two types of defective products often occur. One, underburnt lime. Insufficient firing temperature, resulting in incomplete calcination. It is like undercooked rice. There are still undecomposed particles inside, which results in reduced binding capacity. 2. Overburnt lime. Excessive calcination, meaning it has been overheated. A dense, vitrified shell forms on its surface. making it difficult for water to penetrate and causing very slow slaking. Overburnt lime is particularly harmful. When lime mortar has already been applied and hardened on walls or pavements, the overburnt lime may begin to slowly absorb moisture from the air and undergo slaking. As its volume expands, it can cause bulging and cracking of the surface, commonly referred to as lime popping. How can this problem be addressed? It is essential to carry out a process known as aging. After quicklime is slaked into lime putty, it should be stored in a slaking pit for more than 2 weeks. This allows sufficient time for the overburnt lime to fully slake. At the same time, the water level in the pit should remain above the surface of the lime putty to prevent carbonation. There are 2 ways to classify lime. The first is based on the content of magnesium oxide. If the magnesium oxide content is less than or equal to 5%, it is called high calcium lime. If the magnesium oxide content is greater than 5%, it is called magnesian lime. According to the processing method of the final product, lime can be divided into 2 main categories with 4 forms. The first category is quicklime, whose main component is calcium oxide. The product obtained directly after calcination is lump quicklime. When the lumps are ground into a fine powder, it becomes ground quicklime. The second category is slaked lime, whose main component is calcium hydroxide. When quicklime is slaked into a dry powder, it is called hydrated lime powder. When it is fully slaked into a paste-like slurry, it is called lime putty. As shown in these images, they correspond respectively to lump quicklime, ground quicklime, and lime putty undergoing aging in a slaking pit. Next, let's examine the slaking and hardening of lime. Slaking, also known in engineering as hydration, is the process in which quicklime reacts with water to form slaked lime, calcium hydroxide. This process has 2 notable characteristics. First, it releases a large amount of heat, so it must be handled with care. Contact with eyes can cause severe burns. Second, it involves volume expansion. Large lumps of quicklime disintegrate into fine powder. Now, let's examine hardening. The hardening of lime mortar mainly relies on 2 mechanisms. Crystallization. As water evaporates, calcium hydroxide crystallizes out of this saturated solution. Similar to the recrystallization of crude salt, the interlocking of crystals generates structural strength. Carbonation. Calcium hydroxide reacts with carbon dioxide in the air to form hard calcium carbonate. This is a relatively slow process. According to the content of effective calcium oxide and magnesium oxide, lime is classified into 3 quality grades: premium grade, first grade, and qualified grade. Based on these principles, we can summarize the 4 major properties of lime. 1. Good water retention and high plasticity. Lime mortar exhibits a lubricant-like effect and effectively retains moisture. The well-known difficulty of pulling one's foot out of the lime pit is due to this property. In engineering practice, lime putty is often added to cement mortar to improve its workability. 2. Slow setting and hardening with low strength. Lime-based finishes dry slowly and develop only limited strength, making them unsuitable for load-bearing applications. 3. High volumetric shrinkage. This is the main drawback of lime. As water evaporates, significant shrinkage occurs, so pure lime mortar used as plaster is prone to cracking. Therefore, sand or paper fiber is usually added to reduce shrinkage. 4. Poor water resistance. As a non-hydraulic material, lime softens and may dissolve when exposed to moisture, making it unsuitable for damp environments. Next, let's look at a real engineering failure case. Before we begin, take a moment to think or discuss. Where did the problem occur? The issue lies in the word immediately. As we know, quicklime inevitably contains some overburnt lime, which slakes very slowly. When workers applied the lime mortar to the wall, The overburnt lime was still dormant. By the time the mortar had already hardened and set, the overburnt lime began to slake, causing significant volume expansion and ultimately leading to cracking and spalling of the wall surface. This case painfully demonstrates that quicklime must undergo at least 2 weeks of aging before use. Skipping this step introduces serious quality risks. Although lime has its drawbacks, it becomes a valuable material when used appropriately. 1. Lime mortar, used for masonry construction or interior wall plastering. 2. Lime clay mixture and lime sand clay mixture. The two mixtures are mixed and compacted. In damp environments, lime reacts with the active substances on the surface of clay, producing compounds with hydraulic properties. The famous Fujian Tolu and many ancient tombs were built using a sticky rice lime sand clay mixture, and they have remained durable for centuries. 3. Silicate products, such as sand lime bricks, in which lime provides the calcium component. 4. Carbonated lime boards. Lastly, let's discuss the storage and transportation of lime. There are 2 critical red lines everyone must keep firmly in mind. First red line: prevent moisture intrusion and deterioration. Quicklime readily absorbs moisture from the air and turns into slaked lime, and then continues to absorb carbon dioxide to become calcium carbonate. Once it turns into calcium carbonate, it essentially reverts to powdered limestone and completely loses its binding capacity. Therefore, lime should not be stored for long periods and must be strictly protected from moisture. Second red line: prevent fire and explosion. As mentioned earlier, quicklime releases a large amount of heat when it comes into contact with water. If it accidentally becomes damp during transportation, the heat generated can easily ignite surrounding materials. Therefore, it is strictly prohibited to store or transport lime together with flammable or explosive substances in order to prevent fire hazards. Let's return to the question we raised at the beginning of the class. Non-hydraulic cementitious materials can harden only in air. Once exposed to moisture or immersed in water, their strength decreases, or they may even fail. In contrast, hydraulic cementitious materials are amphibious. They can not only harden in air, but also harden in water and maintain their strength over the long term. As a non-hydraulic cementitious material, lime has distinctive characteristics. It retains water well, but develops low strength. It hardens slowly and undergoes significant shrinkage. The most critical issue to watch for is the delayed slaking of overburnt lime, which can lead to cracking and spalling. This risk must be eliminated through proper aging. By mastering these properties, we can make full use of lime's advantages while mitigating its drawbacks in engineering practice, allowing this ancient material to gain renewed vitality. In the next lesson, we will continue with another remarkable non-hydraulic material, gypsum, and explore its unique characteristics. Thank you, everyone.